For today's project, I'm going to be doing something really weird. I'm going to be turning literal stainless steel forks into a toxic orange salt called potassium dichromate. Potassium dichromate is toxic, corrosive, mutagenic, carcinogenic, along with a bunch of other hazards, so it makes sense that I would want to make it. The only reason this transformation is even possible is because stainless steel is made up of 18% chromium, which is a transition metal which has very good corrosion resistance, which is why it's commonly used in things like forks. If I'm able to isolate the chromium and build it up into potassium dichromate, then this is how the conversion is possible. To start, I grabbed a couple of forks from my mom's kitchen and I broke them in half using my strong hands. This increases the surface area, making the next step easier. The first thing I need to do is dissolve the forks in some sulfuric acid. So to do this, I first filled a beaker with 400 milliliters of water, I added my fork pieces, and then I poured in a total of 100 milliliters of sulfuric acid. It's important to add the sulfuric acid very slowly because the addition generates a bunch of heat and it can easily boil over. So I add the sulfuric acid over the course of around half an hour. You can see the mixture slowly turning dark green as the sulfuric acid reacts with the iron and the chromium to form their corresponding sulfates. Just as a quick demonstration, this is what sulfuric acid does when it comes into contact with paper. Anyways, I keep slowly adding the sulfuric acid bit by bit until I've added the whole 100 milliliters. It took a couple days for the forks to fully dissolve, but in the end I was left with a few pieces of fork remains, which as you can see have a few holes in them and are much thinner. In the end, 3 grams of the forks didn't dissolve, so out of the 70 grams I started with, I only dissolved 67. So I'll have to base all my future calculations upon 67 grams instead of 70. Once all the forks dissolved, I poured the solution into a separate flask. As you can see, there were a bunch of dark green-blue crystals left in the large beaker. This is all iron sulfate and chromium sulfate, which have crystallized out while the reaction was going on. I now need to extract all the chromium out of this, since there's still quite a bit in here. So to do this, I'm going to recrystallize it. I started by dissolving all these crystals in a minimal amount of boiling hot water. Once they all dissolved, I put them all into a smaller beaker and covered the top and let it cool down slowly for crystals to form. Once it cooled down to room temperature, I put it in an ice bath to fully crystallize the stuff out. After a couple hours, I decanted off the liquid into a separate beaker, and as you can see, we have a nice big chunk of crystals in the original beaker. These crystals are now enriched in iron sulfate, as most of the chromium has been washed out into the other beaker. The iron sulfate crystal came out very beautiful, and here are a few up-close shots of it. We're now left with a dark green chromium-enriched solution. To it, I added the chromium solution that we decanted off after dissolving the forks. The solution still contains a bunch of carbon powder which came from the stainless steel, so we filter it off to get rid of this carbon. Once it all filtered through, I pour it back into a clean beaker. I now need to add a bunch of sodium carbonate. This is done to neutralize the remaining sulfuric acid and convert the iron sulfate into iron carbonate and the chromium sulfate into chromium hydroxide. The chromium reacts with the sodium carbonate to form chromium hydroxide instead of chromium carbonate, since chromium ions are so acidic they can't form a stable bond with a carbonate ion. So it hydrolyzes into water and forms chromium hydroxide. I keep adding sodium carbonate until no more bubbles form. As you can see, we have a dark green mixture of chromium hydroxide and iron carbonate. The next day, some of the mixture turned orange. The little bits of orange color are due to the iron being oxidized into trivalent iron, which has this orange color. Anyways, I now need to filter and collect this sludge. So I assembled this filtration tree with 3 different funnels. And I filter everything through, which took a long time. Once it all filtered, you can see that we have a brown and blue mixture of sludge. The brown part is the iron carbonate, which is oxidized, and the greenish blue part is the chromium hydroxide. I pour all this sludge into a larger container and wash the container with some water. Right now, the chromium is in its 3+ oxidation state, which is pretty harmless. To oxidize it to the +6 oxidation state, which is the toxic one, I need to use the hypochlorite ion. So I measure out 70 grams of calcium hypochlorite, which can be commonly found as a pool chlorine tablets. I then dissolve the hypochlorite in some water. We now pour this calcium hypochlorite into our sludge that we filtered out earlier. The calcium hypochlorite is going to react with the iron carbonate to form iron hydroxide, and with the chromium hydroxide to form calcium chromate. This reaction also produces chlorine gas, so this has to be done in a well-ventilated area. I let it react for a couple of hours, and then I filtered it off again. The calcium chromate is soluble in water, and it will pass straight through the filter as a solution. However, the iron hydroxide is insoluble, and so it will remain stuck in the coffee filters. This is how we separated our chromium from the iron. I filtered everything a couple of times through some coffee filters, and I was left with a orange solution of calcium chromate. This solution also contains a bunch of calcium chloride from the other reactions. The next step is to boil off all the water. In the end, I was left with a yellowish-orange crust at the bottom of the beaker. This is all the calcium chromate mixed in with some calcium chloride. I now add some water and mix it in to dissolve it. I know what we did seems useless, like why did we boil down the water to then redissolve it, and that's just to get rid of any volatile impurities. Once it all dissolved, I start adding some concentrated sulfuric acid. Sulfuric acid makes the solution acidic, which forms the dichromate ion. In alkaline or neutral conditions, the chromate ion dominates, but when the solution is acidic, the dichromate ion forms. We add excess sulfuric acid so that the calcium chromate forms calcium dichromate, and the excess sulfuric acid makes it turn into dichromic acid, making the solution red. I tried testing the pH, but the sulfuric acid completely destroyed the pH paper. Now that we have formed dichromic acid, I add potassium hydroxide, which will react with the dichromic acid, forming potassium dichromate. Here I'm using a concentrated solution of potassium hydroxide, so it's important to do it slowly because otherwise it'll boil over. As you can see, the reaction is very violent, and as soon as I pour the solution, it boils. At a certain point, the solution became too alkaline because I added too much potassium hydroxide, and the color went back to yellow. This means that the dichromate ion has disintegrated and formed the chromate ion, which is bad. To fix this, it's quite easy, and I just have to add a bit more sulfuric acid. As you can see, the color quickly goes back to orange-red. I now need to again evaporate the water. After a bit of boiling down, some stuff precipitated. The precipitate was yellow in color, but this was not any chromium compound. It's yellow because it takes in the color of the potassium dichromate. This compound is probably just calcium hydroxide, which formed when the potassium hydroxide we added earlier react with the remaining calcium ions in the solution, forming calcium hydroxide. So to fix this, I just filtered it out and drained the water into a separate flask. I then kept on boiling off the water. After a while, some more stuff precipitated, which was still not a chromium compound, and it was probably still calcium hydroxide and some potassium sulfate or potassium chloride. So again, I filtered everything through the coffee filter, and I kept boiling it down. I know that the precipitate isn't a chromium compound because, as you can see, when I spray water on it, the color disappears. This means that it's a transparent salt, and chromium salts are colored, so this is still probably potassium sulfate, potassium chloride, or calcium hydroxide. As the volume got smaller and smaller, I transferred it to a smaller beaker and kept boiling it down even more. As you can see, the solution has a pretty dark red color, which indicates a high chromium concentration. I filter it one last time into an even smaller beaker, and then we're almost done boiling it down. Once the volume was close to around 40 milliliters, I put it into an ice bath to see if any potassium dichromate would crystallize. Long story short, it didn't, so I kept boiling it down to a volume of around 20 mils. I again put it in an ice bath, and this time finally I got some crystals. I filtered them off and put them into a tiny bottle. It's still quite wet, so I had to dry it. So I left it on my hot plate for a few more minutes, and as you can see, I got some nice and more dry orange potassium dichromate crystals. Aren't they beautiful? Once they were dry, I put them into a nice little bottle, and I labeled it. This project took me over a month to film, which is by far the longest project I've ever done on this channel. I would really appreciate if you liked the video and subscribed, because that really motivates me to make long projects like this. Now we're left with a bunch of waste which I have to deal with. All this waste can't be thrown down the drain or in the garbage because it contains hexavalent chromium. To neutralize all this waste, I made a concentrated sodium metabisulfite solution. As you can see, when I add it to my waste, which was orange, it quickly turns to green. What's going on is the sodium metabisulfite is reducing the hexavalent chromium into trivalent chromium, which has a green color. Trivalent chromium is much more safe and not nearly as bad as hexavalent chromium. This makes the waste a lot easier to deal with and a lot safer. So I soaked everything that came into contact with the chromium in metabisulfite solution. Gloves, filter papers, beakers, stir bars, stir rods, everything was soaked in metabisulfite. This waste can now be dealt with as regular chemical waste without having to worry about bioaccumulation and high toxicity. Overall, this project was pretty fun and thrilling, so I hope you enjoyed watching me do all this crazy stuff. I think it's pretty cool that I was able to turn something like forks into such a toxic compound, and projects like these is why chemistry is so fun.